Okay, here we go. Curve sketching. Let's put it all together. Four main things we want to do. First step is to find all of the basics. Just like we did in advanced functions, we need domain, x-intercepts, y-intercepts, and asymptotes. So we'll look at this first example. It's pretty giant. It's just a polynomial though, however. So right off the bat, domain is all real numbers. Vertical and horizontal asymptotes, we don't have any. Now there is some major factoring using your factor theorem from MHF here. I would suggest if you want to fit all your work on this one page that you have a separate page off to the side where you just do all of your factoring. You can do it with rough form and not worry too much about it. And if you do have questions about the factoring, maybe you can just email your teacher separately and ask questions about that part. Okay, so I'm going to start a little bit over here. Remember, this is a polynomial. Okay, you can even be thinking about its degree. It is degree 4. It has a positive leading coefficient, so our end behaviors are both up. In other words, our end behaviors are quadrant 2 to quadrant 1, right? No asymptotes, as we said. Y-intercept is 0, negative 18, right? And we're going to need to start to factor this to find the x-intercepts. Okay, so again, do the best you can. Pause the video. Do this on a separate piece of paper if you can. I'll lead you through just a little bit of it. First factor, 1 works. F at 1 equals 0. Therefore, x minus 1 is a factor. Then I'm going to go ahead and set up my synthetic division. I have a 1, a negative 5, a 1, 21, negative 18. Bring down the 1, minus 5, then we're subtracting. So we're going to get minus 4, then positive 4, subtract to get minus 3, positive 3, subtract to get 18, and of course here we get minus 18, so we have a remainder of 0. Okay, so what does that tell me so far? That tells me that this factors to be x minus 1, and then our quotient is x cubed minus 4x squared minus 3x plus 18. And then we need to take this and we need to let that be, let's say, a g of x, and we need to factor that further. And I'm going to let you go ahead and do that at the side of your page and get that one factored. I'll give you a hint. 3 works. Go for it. Okay, so given that 3 works here, we have an x minus 1 still. That means we have an x minus 3. And then our quotient, what's left from that division, we should get this. We can factor that further to be x minus 3, x plus 2. That means in factored form, it looks like this. Remember that squared indicates to us that for our x-intercepts, we have an x equals 1, we have a negative 2, and we have a 3, and remember that's a bounce, right? A 0 of order 2. All right, that was all your advanced functions work. Time to move on to step number 2, and let's look at the first derivative, find intervals of increase and decrease, and local max-mins. All right, first derivative. Just using the power rule, 4x cubed minus 15x squared plus 2x plus 21. Let's go ahead and set that equal to 0. We're going to need to solve for x to find our critical numbers. And again, you will note that this is a cubic function that we are solving, so you are going to need to use factor theorem to factor it. Again, pause the video, do that on the side of your page, and come back and see if you got it right. Okay, should work out to be in factored form, x minus 3, x plus 1, and then we've got a 4x minus 7. So our critical numbers are x equals negative 1. We have a 7 over 4, which is a 1.75, and a 3. You're ready to go ahead and make your interval table. Okay, and there's my interval table. Let's put in a number like negative 2. We got negative, 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 overall negative, decreasing function. Here I can put in 0, negative, positive, negative, overall positive, function is increasing. Let's put in a number like 2. We have negative, positive, positive, happens to be decreasing. Put in a number like 4, we're positive, 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 overall positive, increasing. Okay, so we got lots of local max mins here. Here we have a minimum, okay, at -1 comma something. Here's a max at 1.75 if you like, comma something. Feel free to move straight to decimals at this point. And here we have another min at 3 comma, oh wait, this is an intercept, this is 3 comma 0, right? We already know that point over there. Go ahead, find those y values. You should end up with -32 for the min and approximately 4.4 for the max there. Okay, there's all our first derivative information. Time to move to the second derivative. Okay, it's a polynomial, so really easy to take that derivative. We get 12x squared minus 30x plus 2. Set that equal to 0. We're solving for possible inflection points. And this one doesn't factor, so go ahead, use the quadratic formula and get some decimals. Okay, so when I did that, I got approximately 2.43 and 0.07. And again, we're graphing, so these are very approximate. These are our possible inflection points. Let's go ahead and make an interval table with that. Okay, so this is what I got for my interval table. This means, of course, that this is concave up. This is concave down. This is concave up, and that means that we do have 2 inflection points. Here we have an IP at 0.07, find the y value, and here we have an IP at 2.43, find an approximate y value. And so when I did that, here I got a number like 2.06. Here I got something like -16.5. Okay, so that's all your math up to this point. The key step is now we're going to look at putting this all together. Okay, so my first is I'm going to start scanning from the top and I'm going to start plotting points. So let's start first with our y-intercept at 0, -18. We also have our x-intercepts. We have x-intercepts at 1. Watch this scale. We have x-intercepts at 3. This one is also happens to be our min. And don't forget it's a bounce as well, okay? And we also have an x-intercept at -2, okay? Then I'm going to go to my max mins. We already plotted the 1. We have another min at -1, -32. So -1, -32 is somewhere in here. And we also have a max at 1.75 and about 4, just over 4. So that's also a max. 1.75, let's say, comma 4. Also, I have inflection points, so I have one at about 2.4, maybe somewhere around there, and about 2, so that's an IP. Okay, and then I have another one at 0.07, so just after here, and -16.5 should be somewhere around here. That's an IP. Okay, so I start working with my concavity table first, and then I use my increasing and decreasing to verify. So looking at my table, I know it's concave up all the way from the left, all the way to that IP at 0.07. So I can go ahead and I can draw a concave up all the way. Of course, you want to draw a nice smooth curve. That wasn't very smooth, but a nice smooth curve that whole way. I'm also concave up all the way from 2.43. Okay, and I know this min is a bounce, so it's going to bounce back up over here like that. Okay, again, using my fact that I know my end behaviors are quadrant 2 to quadrant 1. Okay, and I'm concave down, so I'll do that one just in red. I know that I'm concave down between those two. So I think you can picture that it's going to look like that, okay? Now I'm going to trace over it, and I'll do that in yellow, just verifying my increasing and decreasing. So I should be decreasing all the way down to my min at -1, and then I should be increasing all the way up to my max at 1.75, and then I'm decreasing just down to 3, and then I'm increasing again. So I sort of use that table to help verify, and voila, even based on what you know from advanced functions, we know this is quartic, positive leading coefficient, there you go. So, of course, the key part of today is making sure that you can take all of that math and you can come up with a very accurate sketch like this. And I do quickly want to just show you one other type of question, just in terms of sketches and being able to interpret the terminology and the math and the symbols. You'll try some of these in homework, okay? So let's take a look at the first one. F prime of x is greater than 0 when x is less than 0. F prime of x is greater than 0. That means that the function that we're going to draw is increasing, right, up until 0. And then f prime of x is less than 0. That means the function is decreasing after 0. And they give us this lovely point here, 0, 4. So here's the point 0, 4. And we know a function is increasing up until that point and then decrease. And sometimes there are different options, but hopefully it's just about interpreting the math here. Let's try another one. F double prime of x is less than 0 when x is less than -1. So this means concave down, right? So we're concave down up until x equals -1. And then at -1, we switch to concave up. So we're concave up after that. So that means that there's an IP at x equals -1. Okay, now we have a little bit more information right here, and that's about the first derivative. So the first derivative at -3 equals 0, and the first derivative at 1 equals 0 as well. So that means the slope of the tangent line at those places is 0, and so these are likely max-mins, right? Or we're going to draw them. There are some exceptions to this, but that's kind of the idea that those could be max-mins. So let's put some values on our x-axis. Okay, we are concave down all the way to -1, and we have a max at -3. Since we're concave down, here's our IP, and then we're concave up, meaning we have slope of a tangent line or a min at 1. Okay, so that's kind of the idea there. There's an example of that one. So try a few of these. They're good for your interpretation. Now, you will notice that I put one more question in here because I just wanted you to see how putting together a sketch of one that was rational looked. I do want you to go through all of the work on your own, and I'll make sure to post a file on our site with a detailed solution so that you can check your work and ask any questions that you need. Okay, good luck with this, and keep practicing those graphs.